So hi everyone, my name is Gilles. I'm a PhD student in University of Caen-Normandie in France. So this project is part of my PhD, and as 10 minutes is quite short, I made it really to the essential so that you can get the essence of what we are doing. So we are working on electric field imaging, and we are trying to apply some detection to non-conductive objects. So, in essence, ça c'est dommage. Can I put this? Can I ignore this part? Yeah. Okay. So basically, what problem are we trying to solve? The problem is to detect change of dielectric permittivity in first an homogeneous medium. So this is a simple schematic so that everyone sees the situation. So we are in a medium, which will mainly be air, and we are trying to detect a third medium that is encapsulated in so the medium 2. So to talk application, mainly we have two things. We have object detection, in which the medium 1 is air, medium 2 would be soil, medium 3 would be the buried object to be detected. And we could also have non-destructive control, which is medium 1 air, medium 2 the body of interest, and medium 3 would be an anomaly. So which physics principle do we use? So let's first start with electromagnetism in matter and use this relationship which is constitutive to the material and the medium equations. Okay, so then we can go from this equation to the polarization density. And in fact, our problem would be solved because we have the polarization density of the medium, the external electric field imposed to the medium. And if we could measure both vectors, then the problem would be solved. But we can only measure superposition of electric fields. So we have to think a bit more. So we have access to the measure of global field. And we have to subtract the information of the primary field that we will actually create to have access to this polarization density, and then we get back to the dielectric permittivity. So this problem makes emerging the technological solution that we have to use. First, we have to have a controllable electric field source with an electric field that is easy to compute and easy to predict. That's really important. Then we have to have an electric field sensor with good performance, even in the low frequency range, and that is not quite obvious. And obviously conditioning electronics and adequate post-processing for the signal. So then basically it will be this setup. We have a source, we have the object, a primary field, secondary field, which is the response of the object to the primary field. We also have background fields, and we have the sensor, and all of that will be our setup. So this is a picture that you will understand, but this is the technology that we use at our lab. So you have the sources and the sensor. So actually about the source, so both source and sensor are internally developed at my lab in my team. And the idea was to go from the charged conductive sphere floating in space, which is a theoretical problem. And so you could have it in a theoretical world, or a world with Jedi Knights, when you have like Master Yoda that is just like pushing it there, and then you would have this great potential map, and that would be a simple field geometry. So then again, it would be really great. But how do we go from there? Because in our world, we have to get charges to the sphere. So the electric field lines are actually distorted. So that's not good for us. And if you want to be not in static, but in variable regime, then you have to have a charge extraction. So it's even making it worse. But so one of the researchers of my team had the idea to actually do a charge extraction that is in a conical shape. So that when you use the law, the Ohm's law, local Ohm's law, so J equal sigma E, you actually can make the electric field lines get perpendicular to the return of the extraction charges, and we do have this mimic of the charge conductive sphere floating in space. So for the sensor, same thing. You could say, okay, to measure an electric field, I just use 2 plates. But when you have multiple conductors, you have influence between them. So we used the guard ring method with the contour electrode and then a reference electrode that is like at a null potential to actually isolate different conductors. So this gives you the one axis design. And we got from one axis to 3 axes. And so then again, the sources, the sensor, which give us our test bench, which is actually the association of the 4 sources that we call poupette. And then the sensor, which is in the middle. And this picture is actually showing the case of a non-destructive control with a body of interest, which is a simple object printed with PLA. So, and so the bench can move and scan, so we do imaging. So what do we expect? So we did some COMSOL simulations with the electrostatic module at first. So here's the, you can see how like the electric field lines are distorted, just like the magnetic field line would be with a magnetic material, but this is with the dielectric. And when you scan, you expect something like that. So we are looking to the in-phase electric field response. And this is the in 3 axes, so X, Y, Z, the projection. And when we do the experimental scan, it's actually pretty good in terms of compatibility. We are able to detect the object, the medium 2, but we don't have a detection of the anomaly. So the question was, do we have a lack of resolution, or is our problem poorly parameterized? So lack of resolution, it's not that. It's always better to get a better resolution, but this is not what simulation told us. And actually, it's just that at one point, I just understood that my result was independent of frequency, which is simple because I was using the electrostatic module. But you know, sometimes you're just like in your computer and you don't see the basic things. So this is not acceptable. And actually, the problem was not well parameterized because we, in my team, the people that develop that are not actually physicists. So they are really, really good at electronics though. So this is where we brought back the physics. We are getting the permittivity, the complex permittivity. And then when we get this complex permittivity, that gets a conductivity because what we call non-conductive medium are actually really, really low conductive medium. You can go like to 10 to the power of -7 Siemens, but it will still have an impact on the results. So then when we get all of this in the right order, we actually can have the picture that I was showing, the result that I was showing before, which was the in-phase response. So we are using a lock-in detector, and we are separating with the quadrature phase signal. And actually what we observed is that the information of the anomaly of the encapsulated medium is in this images. So in the quadrature phase electric field images. So Then you can apply a deconvolution, which is for now really like a basic kernel that we just like, we wanted to see what it was doing. As my thesis director say, you can see it if you have the eyes of faith. So, and but actually you can see that the information is here, but we don't have the good convolution kernel, and it's a work that we will do. And the different axis on this project is to improve the resolution, improve the deconvolution kernel, and also have increase on the frequency behavior, because we actually, I did not talk about that, but we see that we have resonant frequencies depending on the ratios of permittivity and conductivities, but this was too much for you, so I just wanted to stay to the basics. And I'm so I thank you for your attention, and thank you to welcome me at Hyderabad.